So the title of my talk is Robust Hadamard Matrices and the Unistochasticity Problem. And I try to connect Hadamard matrices to some mathematical problems that also have some relation to physics. So first, let me give you the main motivation. And the main motivation comes from the world of bistochastic matrices, which govern classical processes. So a non-negative matrix, which has sum of all rows and all columns 1, is called bistochastic. And obviously, such matrices will conserve probabilities when applied to a vector of probabilities summing up to 1. And when we have a unitary matrix, we can simply obtain a bistochastic one by taking absolute values squared. And well, given that every row and column of a unitary matrix is normalized, it is no wonder that from a quantum process, which, as we may say, as we know, unitary matrices live in the quantum world, we also have transitioned to the classical world of bistochastic matrices. Now, the problem is that it is not always possible to do in the other way. So, not out of every bistochastic matrix can we create a unitary counterpart. Okay, and I know that there are a lot of mathematicians in here, but I hope it's not going to be boring. Well, there's also some physical motivation in studying these matrices, because imagine a classical walk, so that you have in which you have a chain of nodes. Suppose your system is at some time in state K, then at the next step of time, it can either stay or move in the other way. So for a very simple system, we know that probabilities will sum up to 1. And we also know that such a system, such an evolution, can be written down using bistochastic matrices. Now, for a quantum walk, consider not a node, but well, a node consisting of a quantum state. And then we would be interested in the question, can we find a unitary matrix with some parameters that will give us the same probabilities? So basically, this is a question very much connected with our classical walk. Can we find quantum walk equivalent to the classical? Well, it turns out that well, sometimes you can do that, but in order to do that, you need a coin, because such a coin will give you an additional degree of freedom. And then with such a coin, the problem of finding a unitary matrix with some phase which is unknown out of a given bistochastic matrix is also a problem connected to finding a quantum walk with a coin which would be equivalent to the classical one. Okay, that's one approach. The second one that also comes from physics is the problem of determining whether some measurements are feasible given our theory. What does it mean? Suppose we have our theory which describes transformation between different quark quantities, then underlying evolution is unitary. But what we measure in the lab are not complex numbers. We never measure them. What we measure are transition probabilities, and these are given exactly by bistochastic matrices. So in a sense, by investigating the transition between bistochastic matrices and unitary ones, we can also tell a lot about our theory, our physical theory, which tries to describe. Okay, so having this motivation in mind, let me move on to little mathematics, well, very simple one. So first, the definition. We say that a given bistochastic matrix is unistochastic if it has a unitary counterpart. We also know that some of the matrices are unistochastic. For example, any permutation matrix. That's quite obvious since, well, it's obviously bistochastic, but it's also unitary. Okay, what about flat matrix, which is somehow central in the set of bistochastic matrices because all the elements are equal. Sometimes people also call it van der Waals matrix. Does it have a unitary counterpart? Suppose everyone knows that it's very simple. You just take the phases given by the root of unity and you obtain a Fourier matrix. Now, these two examples are positive, but we have also some matrices which are not unistochastic. For example, Birkhoff. Suppose out of this matrix, we create a unitary one with the same, with amplitudes given by the numbers, but with unknown phases. Then what we can do is we can verify whether it's unitary or not. So in order to find whether it's unitary or not, for example, one can take first and the second row, and then what we have is that the product is not zero, never zero actually, under any choice of phases. So we know that this matrix cannot be unitary. Okay, this little and simple characterization can be also extended, and the extension looks like has the very same reasoning. So suppose you take your bistochastic matrix and you try to create at least a unitary matrix out of it. So amplitudes are given by square roots. Now, we know that for a unitary matrix, the product of any two rows, well, must be equal 0. So we take the amplitudes of and square root of AD, BF, and CG, and we know that given some phases, so basically on a complex plane, we can just arrange those numbers in a triangle, and the angles of that triangle will give us the complex spaces necessary. But when it's only possible when the numbers, well, when out of these numbers we can create a triangle, because sometimes not every free number can give us triangle. And similarly, for higher dimensions, this will not be triangle, but polygon, in general, a polygon. Now, this condition must be valid for any pair of rows and for any pair of columns. And if it is so, we call such a matrix a bracelet matrix. Obviously, bracelet matrices, in our case, bracelet bistochastic matrices, will be at least as big a set as unistochastic ones, because every unistochastic matrix is necessarily a bracelet. And we know for some time already that in dimension 3, it is also a sufficient condition. So any bracelet matrix is also unistochastic. These two sets are equivalent, are the same. And in here on the figure, you can see cross section through the set of bistochastic matrices of dimension 3 with corners given by permutation matrices. The green set is the set of unistochastic matrices, and the red points are bistochastic matrices, which are not unistochastic. Okay. The problem is that this simple characterization is no longer valid in higher dimensions, say dimension 4. In this case, we have quite strange geometry, because the central point of the set of bistochastic matrices, the flat matrix, is also on the border of the unistochastic set, because it is possible, starting from this flat matrix, which we know has some corresponding Fourier or any Hadamard matrix, we know that we can choose some direction, in here written as B1, and go infinitesimally small in this direction, and we will leave the unistochastic set. But obviously, well, it's not maybe that obvious, but it can be easily shown that the matrices around will still be bracelet. So this set are no longer equal. Now, even though we don't have an analytical construction of that, we have found an algorithm, well, guided by the late Uffe Hagerup, that allows us to find, allows us to verify whether a given Foiberg for stochastic matrix is unistochastic or not. Well, the algorithm is basically, the idea for that is to divide the matrix into 4 blocks, and then using orthogonality relationship between those blocks, we are able to determine whether the matrix is unistochastic or not. So at the end, if you're interested in that, in the bottom of this slide, there is a URL which will lead you to the algorithm we have created, and which you can use to verify the unistochasticity of any 4x4 matrix. Okay, because we are studying the unistochasticity problem, and we have focused on some smaller, well, simpler problem of determining the set of bracelet matrices, we are tempted to compare how do these sets, well, which one, how larger is the set of bracelet matrices. So it is interesting because in the case of dimension 2, for matrices of dimension 2, all bistochastic matrices are unistochastic. For dimension 3, as I told you, not all of them are unistochastic, but all unistochastic, well, all bracelets are unistochastic. So the set of bracelet and unistochastic is the same. But for higher dimensions, this set do not coincide. And actually, after 4, we don't know anything about the volume of the relative volume of the unistochastic set, but we know that because it is fairly simple to characterize that the bracelet set asymptotically goes to 1. So in the case of large matrices, almost all of them satisfy these bracelet conditions. Now, some of you have been talking a little about circular matrices. And here we have also done some research in the case for circular matrices which are unistochastic, and we're particularly interested in the question: will the bracelet conditions help us for circular matrices? So first, we know that for 3x3 circular matrices, all bracelet ones are unistochastic, because, as I told you, this is true for all bracelet matrices in this dimension. However, for a general 4x4 matrix, it's no longer the case. But we have proven that those which are circulant, for those which are circulant, this is true. So, in other words, you can say that because of asymmetry, all circulant matrices of bistochastic matrices of this dimension somehow are easier to characterize. And in here, what you can see, well, there is the tetrahedron of circulant matrices of dimension 4, bistochastic circulant matrices, and the corners are permutation matrices. Green set is the set of unistochastic and also the bracelet matrices. And on the right, similarly to Roberto, we also have printed, 3D printed this set, and I'm particularly happy that we have done it, because not always developing some mathematical, quite abstract things, you are able to, at the very end, to find something that you can hold in your hand. And I'm thankful to our colleague Konrad, who did it, who's really good with 3D printouts. Okay, this was some things not that much related to Hadamard matrices, but the problem of unistochasticity can be also handled from perspective of Hadamard matrices. That is, Hadamard matrices will help us say something about certain subsets inside Birkhoff Polytope, which is the Polytope
formed by isoelastic matrices. So we have a central matrix W, the flat matrix, the van der Waals matrix, and we define rays. So ray is any line from the central matrix to any corner which is given by any permutation matrix. So there are quite a lot of rays in Birkhoff polytope of high dimension, and every result that I will cover in here, if it applies to rays, it will also apply to counter rays. So counter rays are the part of a line that extend through W in the other direction. In order to say something about the unistochasticity of rays, let me introduce robust Hadamard matrices. And these are matrices, Hadamard matrices. It can be also complex, they don't need to be real, such that if we take principal minors, they will be non-vanishing. So in here, suppose you have 4 by 4 Hadamard matrix, then there are 6 principal minors. You just need to take 2 diagonal elements and the corresponding off diagonal ones, say this green, and these corresponding to. And such matrix formed by these green elements must be Hadamard if we want our matrix to be robust. And for every 6 possibility, we want it to be so, and then such a matrix is robust. Okay, this is some definition. Now, do they exist? Yes, they do exist, and the construction is pretty simple, especially for those for which there exists real Hadamard matrix, and for those dimensions for which there exists a skew Hadamard matrix. So skew Hadamard matrix is such a matrix that when we take H and add to it H transpose, then it's only the identity. So all the off-diagonal elements will vanish. Very simple observation is that if we take skew Hadamard matrix, it's automatically robust. Because when we take the elements on the diagonal, there will be all ones, and on off diagonals there will be of opposite signs. So very simple. Similarly, when we have real symmetric conference matrices, it is also possible to create such robust matrices, now complex, in different dimensions. But it is slightly more complicated. So, well, not much, but if you want to verify it, read more about it, I refer you to this paper. And what can we use them for? Well, take matrix from array. Suppose we take the simplest array, the array between the flat matrix and identity matrix. Obviously, the form will be particularly simple. There will be elements A on diagonal for some A and B off diagonal for some B. Now, we want to find unitary matrix that will correspond to it, and it turns out that you only need to multiply element-wise the matrix formed by square root by the robust matrix of this dimension. And then, for example, here I have taken skew Hadamard matrix. So obviously the sign on the diagonal is not changed because these are only ones. Off diagonal we have, if here there is plus, there is minus here. If here there is minus, it's plus over there. So actually, in the very same paper that I showed you, I've shown you on the last slide, we have proven that this construction automatically gives you unistochasticity or orthostochasticity for the case of real matrices. So orthostochasticity is even stronger than unistochasticity because the corresponding unitary matrix is not only unitary but also orthogonal.
And we have proven that for all even dimensions smaller than 20, all rays and counter rays of the Birkhoff polytope are orthostochastic or unistochastic, depending on the dimension. Also, for higher dimensions, for various higher dimensions, we have proven it is true. Basically, it is only given by the fact of whether there exists a skew Hadamard matrix or whether there exists a symmetric conference matrix. And if that's true for a given dimension, then the same will work in here. Okay, so now curious observation that we have also, well, because what we have shown till now is that given skew Hadamard matrix, you can say something about the Birkhoff polytope and the unistochasticity product. But what is interesting is that also the converse is true. So if you have certain matrix on the ray or counter ray, and if you know that this matrix is orthostochastic, so there exists an orthogonal matrix corresponding to that, then by just taking the signs, you will create skew Hadamard matrix. So I would say that possibly this problem is also not easy to find, to verify, but well, if you wish, you might try to tackle the Hadamard conjecture from the perspective of the unistochasticity product. Okay, finally, because I'm a physicist, I also would like to have some problem of which stems from quantum information. And what can we use these arrays for? So in quantum information, we often deal with entanglement when we have, let's say, bipartite systems. So when we have bipartite systems, then we might want to consider different bases which will be used to describe it. For example, there will be separable bases in which all vectors are separable and contain no entanglement at all. But there will be also maximally entangled base, which is a base consisting of vectors which all are maximally entangled. Let's say Bell bases for those which come from field of quantum information. So there's a question: what about the intermediate case? Can we find a basis which will correspond to given value of entanglement, which is not minimal nor maximal, and will all elements of this basis possess the same value, the same amount of entanglement? So it turns out that the matrix which will correspond to the Bell basis, to the maximally entangled basis, is actually the flat matrix. And the unitary matrix which comes out of it is, well, it can be Hadamard matrix, and the separable basis will correspond to, let's say, identity or any other permutation. So if you're able to connect these two by any line which will be unistochastic, by taking those unitary matrices which correspond to the points inside Birkhoff polytope, we will obtain a basis which has the same degree of entanglement. And this is exactly what we were talking about before, because this is exactly the ray of the Birkhoff polytope. By applying Hadamard matrices, we are able to construct some bases that might be of certain interest for someone. Okay, so let me conclude my talk. So I believe that the problem of unistochasticity has a lot of physical, but not only physical motivation. And certainly you can hope to show something more, to try to prove something about the problem, to try to expand your knowledge about it using Hadamard matrices, as we did for rays of the Birkhoff polytope. And with this, I'd like to finish my presentation. Thanks.